All right, we're going to look at multiple covalent bonds and the strengths of covalent bonds and then the general properties of covalent bonds. Next chapter we'll look more at exactly why these properties occur, but for right now we're just going to look at the overarching properties. Okay, so the first thing is multiple covalent bonds in general. Okay, they're sharing more than one pair with another element. So instead of having just one element and one pair of dots, okay, with say a carbon and an oxygen, or a C with one line by oxygen, it'll be multiples. Okay, you have either what we call double or triple bonds. Double bonds or triple bonds generally form with either carbon, nitrogen, oxygen, or sulfur. Other atoms can have them, but those are the ones that tend to do this the most. Okay, so double bonds are just what they sound like. They are two shared pairs, so we have 4 electrons total. So the best example here is oxygen, or O2. So if we look at O2, we have one oxygen that has 6 valence electrons, the other oxygen has 6 valence electrons. So instead of finding 2 spots here to bond, or 2 different things to bond at those 2 spots, each oxygen shares their 2 pairs together. And so we end up with 2 shared pairs there in the middle, or 2 sets of dots, or 2 lines, depending on how you want to draw that one. Okay, so we can think of it as these 4 right there make those 2 double bonds. Okay, now we look at triple bonds. Triple bonds are 3 shared pairs, or 6 total electrons. The best example here is N2. Okay, each nitrogen here has 3 spots where it can bond with something else. So instead of having 3 separate things that's going to bond to, so one N and say 3 Fs, okay, where I have 3 bonds, we're just going to have 3 bonds there with my 3 circles to the other one. Okay, so you have 3 single bonds or a triple bond. All right, we draw that with 3 lines in between, and that one should have another dot on that side. I'm not quite sure why it doesn't. That should be 2 dots and N, 3 lines and 2 dots. Okay, so we have 6 electrons there, or 3 shared pairs. Remember, each line is 2 electrons. Okay, when we talk about the attraction in a covalent bond, okay, ionic bonds were a positive and negative ion, or a positive negative atom. Covalent bonds are the positive nucleus of one atom and the negative electrons of another. Because you don't have a positive negative ion, okay, I don't have one that loses or one that gains, I have one that shares with the other one. So if we have like this example up here with this N and the 6 dots there, okay, you have the positive of this N, the positive of that N, which would be their nucleuses, okay, they're always positive, and we had that same thing in the nonmetal metals for ionic bonds, but it was outweighed by the whole atom being positive. In this case, the whole atom is not positive, just the nucleus is. And then I have all these dots here in the middle that are my negatives. So the negatives that are kind of in between the 2 atoms are what's holding or attracted to the other nucleus of the other atom. Okay, so it's a lot smaller charge here. You're dealing with little bitty particles versus whole atoms that are positive or whole atoms that are negative. So these attractions, or these magnets, they are a lot weaker than an ionic bond. Okay, so it's weaker than an ionic bond by a whole lot. All right, we'll look more at these ionic and covalent along with metallic ones in the next chapter, and kind of why covalents are even more less of an attraction. Okay, so we have the strengths of covalent bonds and their bond length. They go hand in hand. Okay, strength depends on the distance between the atoms. So if I look just at a covalent bond, the longer the bond, the weaker the bond. Okay, and if you have more shared pairs, my length is going to be less. So my triple bond down here with N2 is a triple covalent. See how this size here is smaller. Okay, 1.1 times 10 to the negative 10th is a lot smaller than 1.4 times 10 to the negative 10th. So N2 is my smallest one here, but it has the most shared pairs. So as my shared pairs go up, my distance goes down. The next thing we're going to look at there is bond dissociation energy, which is the next part of that little chart there. Okay, bond dissociation energy is just the energy to break a bond, and we're talking about a covalent bond when we deal with these, not ionic. Breaking an ionic bond is a lattice energy. Breaking a covalent bond is a bond dissociation energy. Same thing with a different name. Okay, the shorter bond is also the stronger bond. So notice here in this table that my smallest bond is here at the bottom, and it is the biggest number. Okay, think of them as being the kind of the closest together. They are sharing the most things, so they are the hardest to break apart. It's kind of like how if you have a magnesium, which is a 2+, and a potassium, which is a positive, the 2+1 is going to be harder to break because they're gaining or losing more electrons here. They're kind of sharing more, which brings them in a little bit tighter. It's a lot harder to break something that is that long versus a single bond, which would be like that. Okay, a longer single bond is a lot easier to break with a lot smaller bond dissociation energy with it. Okay, they are always positive numbers. They're positive numbers in the same sense that lattice energies are always positive numbers because they're putting energy in to break the bond apart. You're not getting energy out, which would be negative. You're putting energy in. So all of these are kind of endothermic processes here where you're trying to put energy in to break the bond apart. Okay, bond energy and reactions, it's either endo or exo based on the bonds that are broken or formed and whether the bond dissociation energy total is positive or negative. So we don't do calculations for these right now, but you can. If you were to kind of go through and count all these different bonds you would have in a reaction, if it took more to form them or if it took more to break them, it could be either endothermic or exothermic. So that's kind of also how they figure out with these reactions, whether they give off heat or whether they don't give off heat. It has to go with how strong their bonds are in that particular molecule. Okay, the last thing here we're going to look at is the general properties of covalent bonds. Okay, you have lower melting points than ionic bonds because they're easier to break. Because like I said earlier, they are smaller positive, negative particles. We're talking about little subatomic particles, not whole atoms that are positive or negative. So they are much weaker. Conductivity, they're not conductive as a solid, and they're not as strong of a conductor when they're dissolved in water as an ionic bond. So they're not conductive at all as a solid, and they're not as strong. Let me put that. They're not a strong conductor. When they're dissolved in water, they're only mildly conductive compared to an ionic bond, which is going to really be conductive. And the last thing is solids. Okay, ionic solids are very brittle. Covalent bonds tend to be softer than ionic. They're not as orderly. You don't have the nice positive, negative crystal lattice here. Molecular bonds or covalent bonds have kind of these crazier different structures, and different molecules have different structures. So you don't have these nice big positive, negative repeating patterns. Covalent bonds do not have that, so they are much softer. So we're going to look at these questions here, and I already have them answered. All right. What is the difference between a single, double, and a triple bond when you look at how electrons are shared? Single is one pair. Okay. A double is two pairs, and a triple is three pairs. Now, if we look at the relative bond dissociation energies needed to break the bonds in your structure below, this one here should be the hardest one to break because it is a triple bond. Okay. The second hardest one should be the double bond. Okay, and the easiest ones to break are any of these carbon-hydrogen bonds. It doesn't matter which one, any of them. Okay, so this triple bond here will have the largest bond dissociation energy, and then any of these CH ones would have the lowest bond dissociation energy. And again, remember, bond dissociation energy just goes with covalent bonds. All right, then if we compare the boiling point and the melting point of sodium chloride versus sugar, this is where you got to be able to tell which one is which kind of bond. NaCl is an ionic bond because we have a metal and a non-metal. Okay, you got Na, you got Cl. It's harder to break and has a larger melting point and boiling point than sugar. One type of sugar is C12H22O11, which is just carbon, hydrogen, and oxygen. So I have a bunch of non-metals here. So those are a lot easier to break than an ionic bond.